Rachel Gold. I'm an aerospace engineering student at the University at Buffalo, and I'll be presenting my research on the lumped parameter modeling of space tethered net with nodes inside of threads. So just a quick introduction. The tether nets are a method of retrieving and disposing of debris from orbit. So you can see a scenario here. I'm just going to explain how they work. A chaser satellite or rocket or whatever you want to use, which has the net stored in it and an ejector, will follow the target object, which could be a defunct satellite or a piece of debris, something like that. And then once the chaser gets close to it, it'll impart a velocity onto the corner masses, which are right up here. And then the net will shoot towards the target, capture it, and then the chaser will have full control to bring that object to a disposal orbit and mitigate the amount of debris in orbit. So these are needed because space debris is a growing problem in Earth orbit. You can see that there's a pretty high density of debris, especially in low Earth orbit, which is right down here. And this can cause some pretty heavy destruction to functional satellites. So a mission that potentially costs millions of dollars could be destroyed by a piece of debris hitting that satellite. And this has actually already happened. And so methods are absolutely necessary to start mitigating the amount of debris in orbit, and tether nets are one way of doing that. So tether nets are modeled because the motion of a tether net is nonlinear and it's pretty unpredictable without some type of modeling. So the lump parameter model, which is the model that I use, is a linear model which describes the motion of a net by lumping the weight of physical threads into point masses along the outline of the net. These are all connected by a massless spring damper system. So you can kind of see what that would look like in simulation right here. And something that's really important to note is that these point masses, they can impart a force because they have mass, and a force can be imparted on them. But this massless spring damper system doesn't have that luxury. It can't impart a force. It's as if it doesn't exist if something were to collide with it. So what I just described is kind of what caused an issue in simulation. So you can see in this image here that, so we have a capture of the ESA satellite MVSat, which is a mission that's completely over. The satellite doesn't work anymore, but we want to capture it and bring it out of orbit. And so what you can see here in this original model, so this is a model created by my advisor, Dr. Eleanor Abada. And what she did is she placed those point masses at knots, which are right here and here, for example, which are the places just in between the threads. And that distance was too large because what that meant was that those thin surfaces of NVSat here could fall right in between those 2 point masses. And it's as if to the simulation, those places did not exist at all. So this wasn't completely accurate, and we wanted to make something that was a little bit more accurate. So my research is to place point masses not just at those knots there, but also at where the threads would be. And so since I made a general model where the distance between 2 points is changeable, we could make that distance then the thinnest part of the object of interest. And so this problem wouldn't exist anymore in the capture phase of the simulation. So this is just a little bit about what the net configuration is. In the original model, there were just the knots. So those X's here, those are what the knots are. And then there was also the corner masses. But any of those red circles, those didn't exist before. And the way that we describe that is the number of knots on a side are n sub k, the number of nodes in between 2 knots, these red right here, is n sub I, and the number of nodes on a corner thread, which includes the corner masses, is n sub ct. And so in this specific example, you can see n sub k equals 3, n sub I equals 2, and n sub ct equals 3. And I could always add more inner nodes or more knots, and I could change the configuration of a net completely. And so this is the equation of motion of the net. So the main thing here is that you have 2 components that can change the motion of the net. You have a tension force imparted on the on the nodes and an external force. So the external force comes into play when you have a capture scenario. So when a point mass hits an object, that's when you have a force exerted on the point mass. And then the tension force is all the time, essentially, after the net is ejected. And so what that means is that you have some initial length between the node and the node next to it, or the multiple nodes next to it. And then once that length between those two nodes becomes greater than that initial length, that's when a tension force is exerted on it. Any other time, this tension force doesn't come into play. And then what I mentioned before was also the lumped parameter part. So if you have a point mass, what you're doing with the lump parameter is you're taking all of the mass around it, so the mass of, say, the threads around that point, and you're lumping it into one point mass. And so that's what this mass model is doing here. So this mass model M sub I right here, that's for, so you have different places in the net. So you have your knots, so you have a mass of a knot, and then the mass of all the threads around it, which is this summation here. And then you have the inner nodes, which is right here. You'll have the corner masses, so again, that's the mass of the corner mass and then the thread around it. And then you have the nodes on the corner thread. And so that's this last one right here. So these summations are general, and they work for any type of net. So just a quick summation of my testing. So I did 2 tests. The first one was just to make sure that the model was equivalent to the old model when there were no inner nodes. So this is the completely same net. So there are no inner nodes, so you just have point masses at the knots again, which is exactly the same as the old net, just with this somewhat changed mass model. So the results of that should have been completely the same, and you can see in this first image here that they are. So that was a great result, and that's exactly what I wanted to see. And the second test was another deployment test, but this time I added 2 inner nodes. And so what I expected to see here was the tension force was going to change a little bit because of these inner nodes. And so I expected to see the basically same trajectory of the X position, but it would be a little bit different in the displacements. And so you can see here in the dotted red lines that there is a little bit of a difference from the original model, but it's very small, and that's exactly what I expected to see. So this was a good test. And just to give you a little bit of a better idea, I created a 3D video showing the motion of the inner nodes model and the original model. And so this is what that looks like.
2 minutes remaining.
So you can see that the inner nodes model does change a little bit from the original model, but it's no more than what's expected. So I just want to present a few conclusions. So the results present evidence that the new model does correctly represent the dynamics of the net based on some validation of the original model. But the complexity of the model doesn't allow for continued use of MATLAB for simulation. The simulations are too large for MATLAB, and they're causing the computer to shut down because of it. So I'm moving the simulation over to something called Vortex Studio, which is based in C++. And Vortex Studio is better for large problems like this. And so that'll be used for all future simulations and also a test of capture. And finally, I'm confident that the results presented here that will improve the capture performance from what we saw earlier, where there were some spots being completely missed. I just want to quickly thank my advisor, Dr. Eleanor Abada, for introducing me to our lump parameter model and guiding me through this project. And I want to thank you guys for listening to me. And if you have any further questions after the session, please just email me at the email I've listed below. Okay.
And time for questions?
Rachel, why is it necessary to have these simulations be accurate?
So if the simulations aren't accurate, then when we actually perform a test with this, so we go up to space and we shoot a net, and we expect this net to go some distance in every direction. So it's a three-dimensional thing. So it wants to go, we want it to hit an object exactly. But if it doesn't hit the object exactly, then we lose the object, we lose the net, and then we have to perform this all over again. And so we want to capture an object the first time. And if we don't have an idea of what the trajectory is beforehand, then we're never going to be able to do that. Does that answer your question?
I've got a question, Rachel. Does your model change depending on whether it's in low Earth orbit versus higher orbit versus in atmosphere? Or is this just a standard model for nets in general?
It's a standard model. It's general. There we can change the force model a little bit, which we have done in the past. We actually did a deployment. We validated the deployment of the previous model a few months ago, and what we did there is we actually added some Coriolis forces to the simulation and some excess acceleration because we were validating against a parabolic flight test. So the model has room to add extra forces if we think that they're significant.
Thank you.